Let's have a look at question 5. It's exercise 10J, page 459. For each function below, that's that one, and that one, find any local maximum or minimum points. Well, when you see maximum, minimum, we're going to think about the first derivative. So we're going to take the first derivative of this function. Now the first derivative of this function is this first half here, this part, times the derivative of the second. And I've done it this way, just to make it clearer. So we had a power 1, it gets to 0, and the derivative of that x is that 1 there, plus the derivative of the second part times the derivative of the first. Well, that's 3 times x minus 2 squared, and what's inside is 1. We tidy this up a little bit here, and then we can see that we can factorise out x minus 2 squared, and that would leave 1 more x minus 2 here for this term, and here it's going to leave 3 times x plus 1. Now we tidy up that, and we ended up with 4x plus 1 times x minus 2 squared. Now, maximums and minimums do occur where the derivative is 0, the tangent is horizontal, and this indicates that it would be here when that term is 0, that would be x is 2, and when this is 0, that would be x equals minus a quarter. Now, use your graphic display calculator, and you can see that there is only one, there's a minimum. This one here is excluded because it's a point of inflection. Okay, that's a point of inflection. Now that's true that the tangent is 0, it is horizontal, and if we investigated it, we could find that to the left and to the right, that the actual slope didn't change. And you can see that on the graphic display calculator, and since we're allowed to use it, let's use it. We'll graph it. We can see that this is the one we're interested in here. That is actually a minimum, and that point is at x equals minus 0.25. Now at that point of 0.25, they've asked us to find the points. So we need to find the y value, corresponding y value. So we put that into here, and we get up y is minus 8.54. Now similarly with b, we have this one here. Now this is a little bit more difficult, and it covers things that we haven't actually done yet. So let's just go through the process. That's our domain. X is greater than or equal to 0, less than or equal to 2 pi. So that's a whole 360. We take the derivative of this. Now the derivative of this is the first one, e to the minus x times this derivative of cosine x, which is minus sine x, plus cosine x times the derivative of this one, which is as it is, and the derivative of this part up the top, which is minus 1. We resolve that, we factorise out minus e to the minus x, and we've got sine x plus cosine x. Now we know that that does never equal 0. There's no value of x for that to equal 0. So we're going to look at this one. We're going to focus on sine x plus cosine x. Now sine x plus cosine x equals 0. That would make that 0. Okay. Now I've drawn the two drawings here for the two answers. Now, what we're looking for here is a value for x that term equals the negative of that term and vice versa. So if you remember from our tables, the sine of 45 is root 2 on 2, and the cosine of 45 is root 2 on 2. So if we consider the first, we're going to start from 0 and we're going around this way. Well, that would happen here. Remember, the cosine is reflected on here. You can see that as a value of cosine. And the sine is this one. So there's our plus root 2 on 2. That would be for 3 pi on 4, okay, because this part here is pi on 4, which is 45. It's in the second quadrant. And at 3 pi on 4, the value of sine is root 2 on 2, and the value of cosine is minus root 2 on 2. Well, that would equal 0. So that's one solution there, 3 pi on 4, which is 2.36. They want the point, so we put that value into this original expression up here, and we find that the y value is minus 0.067. Now there's another point as well, and that's down here. Okay, at this point, the cosine value is plus root 2 on 2, and the sine value is minus root 2 on 2. Now that would equal 0. Now that goes around 7 pi on 4. Remember, 2 pi is actually 8 pi on 4. So if we go around 7 pi on 4, around to here, we get this. So 7 pi on 4 is 5.50. when we put that as an x value back into the original expression, we get the value, well, I've put y, but it's actually h. Okay, the value of the function is 0.00290. That should be h, the function value there. Okay, so that's good. Now let's have a look at this one, c. Again, we're going to take the derivative. Now the derivative of this is the first one, x cubed, times this as it is, and then times the derivative of what's up here in the indice here. That's minus 2, plus that times the derivative of this. Now the derivative of that is 3 times x squared. We get to that line, and then we factorize out e to the minus 2x, and we've got 3x squared minus 2x cubed. Now we're looking for maximum minimums, so again we're going to equate this to 0. Well, there's no situation, no value of x for which that equals 0, so we exclude that. We've got 3x squared minus 2x cubed. That would equal 0, and then that we would have the derivative equaling 0. So we factorize out x squared and 3 minus 2x, and we've got that. So that would be x equals 0 and x equals 3 on 2. Again, we need to investigate these to see if they're true turning points. Is the slope changing from positive to negative or negative to positive? Well, we don't need to do that. We've got the calculator. So put it into the GDC, the original function. Have a look at it. You'll see that there's a max at 1.5, and that this is actually, again, it's a point of inflection where the slope stays the same, but the concavity changes. Now we put x equals 1.5 into this, and we get y equals 0.168. Let's have a look at 2. It said find an expression for the second derivative. So I've copied the first derivative from the previous page, from part I or part 1. And what we need to do now is take the derivative of this. So we can do that by multiplying this by the derivative of that. That's that by 4, plus this times the derivative of that, which is 4x plus 1 times 2 times x minus 2 to the power of 1. And that 1 comes from the derivative of x. Okay, so we just go through the process here. We look for something to factor out. I'm factoring out 2 times x minus 2. These things resolve to 6x minus 3. I can take a 3 out of there as well, and we ended up with 6 outside of x minus 2 times 2x minus 1. For b, I copied this from the previous part, which was part I or part 1. That's the first derivative. Now the second derivative is this times the derivative of that. The derivative of sine is cosine, the derivative of cosine is minus sine, plus this times the derivative of this. Now the derivative of this is minus e to the minus x, and the derivative of this indice here is minus 1. Now again, I'm looking for factors, so I take out e to the minus x. Now be careful, this part comes from there. I've swapped it over because I had a negative sign here. So that sine x plus cosine is here, and that cosine x minus sine x is here. Okay, because I flipped everything around. Can you see what I've done? Anyway, that works from here to here, and they ended up with this 2e to the minus x sine x. Next one is c. Okay, so I took this from the previous part 1, and that's the derivative. We have to find the derivative to get the second derivative, so it's this times the derivative of that, plus this times the derivative of that. I'm going through this looking for factors. I take out e to the minus 2x. I resolve all of this. Resolve that, get to this. I can also take out a 2x out of that. So I've got 2x e to the minus 2x times that. And they're expressions for the second derivative. Okay, and now what we're doing is part 3, find any points of inflection. So I've copied from the previous part the second derivative. Now the second derivative will show us inflections when it equals 0. So we put 0 there, and we equate it to 0, and we say that when x minus 2 equals 0 using the null factor law, then that would be true. And also when 2x minus 1 equals 0, that's true. So we have the x value of 2 and a half. and we put them in at x equals 2 because it says find the points, so I have to find the y value. So at x equals 2, y equals 0, and x equals a half, put it straight back into here, we get y equals minus 5.06. b, okay, I've copied the second derivative from the previous part. When that equals 0, we should find points of inflection. Okay, so what we do is we know that either that's 0, that would be true, then the left-hand side would equal the right-hand side, or sine x equals 0. Well, this cannot equal 0. There's no value of x that's going to make that equal to 0. So let's focus on this one. Sine x equals 0. Well, within this range, or this domain here, that's one full revolution, then 0, sine of what is equal to 0? Well, it's 0, pi, and 2 pi. Okay. And then we'd ask for the point, so we've got to find the y value. When x is 0, or in this case the h value, when x is 0, h is 1. When x is pi, h is minus e to the minus pi, which is minus 0.0432. And when x is 2 pi, h is e to the minus 2 pi, which is 0.00187. Let's have a look at C. Well, I copied the second derivative from the previous page, and now we know that the points of inflection would be where the second derivative equals 0. So I've broken up into 3 parts here. We've got the 2x, we've got e to the minus 2x, and we've got this. Now, if in either of these, any one of these equals 0, this would be true. So 2x equals 0 implies that x equals 0. When x equals 0, y equals 0. So there's a point there. This second one here cannot equal 0, so we're going to ignore that. That can never equal 0. But this one here could equal 0. So we're going to put that there. We're going to use the quadratic formula. And we've gone through here. We get to that. And then this. So we ended up with 2 more, which is this, the plus, and also the minus. We get x is 2.37. And so y is 0.117. And this gives us x is 0.634 and the y value is 0.0717. So those 3 points are points of inflection. Let's now have a look at part 4. It's to determine the intervals where the function is concave up and where it is concave down. Okay, that's not too easy. Use your GDC at the same time. Put that in and just have a look at what the graph looks like. Go back and have a look at the previous 3 parts and find out, just remind yourself where the minimum was, points of inflection were. I've done that for each one. Max, inflection. Okay, once you find that, then you look at the calculator and you know the values. And you can see that for this function here, it's concave up where x is less than a half and x is greater than 2. And concave down where x is greater than a half and less than 2. Okay, again, using the GDC and knowing these things that we discovered in the first 3 parts of this question, we can see that it's concave down where x is greater than 0 and less than pi, and concave up where x is greater than pi and less than 2 pi. And the third one, again, this is hard to see on the calculator. It's kind of very close, hugging the x-axis. But we've got maximums and inflection points from the previous parts. And you can see then it's concave down where x is less than 0 and where x is greater than 0.634 and less than 2.37. And it's concave up where x is greater than 0, less than 0.634 and x is greater than 2.37.